Welcome to Brain Vision.
So I'm going to look at problems 39 and 40 together because they look at the same structure and just want to look at internal forces at two different points. So we have a semicircular rod like this. It's clamped at this end and it's free over here. And then we have a load here that varies like minus W naught sine of theta in the radial direction. So it's always pointing in towards the center here, but the magnitude goes like minus omega naught sine theta. And the radial vector is given by, again, if we use this as theta, is cosine theta sine theta. So that's a vector in the radial direction. Now, to figure out what the equivalent force is on this, we can take this, basically integrate this from theta equals, well, from over here, theta equals 0 to pi. And we see that the equivalent force in the horizontal direction is 0, which we'd expect because of symmetry. And then in the vertical direction, it's minus pi over 2 r omega naught, which is not surprising because that it's negative. Again, we're taking omega naught to be positive here. And then we can figure out what the internal moment, the equivalent moment is by taking a vector to an arbitrary point, which is just r times this vector, and then take the cross product with this vector, and then integrate from 0 to pi. So we have a differential of r d theta. And with this case, you get that this moment is 0, which shouldn't be surprising since all of these forces act through the origin here. So the moment about this point is 0. If we sum forces in the horizontal direction, we get that n1y, or n1, or in the vertical direction, sorry, n1y is pi over 2r omega naught, and 1x is 0, and then the moment is pi over 2r squared omega naught because of this this moment arm here. Right. So we have the or again, if you looked at it from here, it would be the moment arm. If you just took this as the center, and then this moment arm, this load here creates a moment that needs to be counteracted by that. So that's what we get for the moment here at the clamp. Now, for the one problem, they want us to take theta equals 45 degrees, so right here. And then the other problem, they want us to take 120 degrees, so like right about here. So let's take a look at the 45 degree angle. Again, I'm going to say that we have an internal force vector that we don't know. We just have two unknown components to that, and then an internal moment. And so in this case, we need to redo what our distributed load resultant force is. So in this case, we redo this integral here, but from 0 to 45 degrees. And we get that F2 prime, the vector is minus r omega naught over 4, and times the vector, this vector 1 in the horizontal direction, and 1/2 pi minus 2 in the vertical direction. So we shouldn't be surprised that we have both components because there's obviously a net force in this direction, and these are both, this is positive, so these are both negative components, which makes sense. It's in this direction and that. And again, we can redo the integral here from 0 to 45 degrees, and again we're going to get that the moment is 0 because again all these forces act through the center here. Summing forces, we get that N2 minus F2 prime has to be 0. and that tells us that N2x is r times omega naught over 4, N2y is r times omega naught over 8 times pi minus 2. Now we can take the position vector to this point here, so we can take moments moments, and that position vector is just r cosine theta 1 sine theta 1, where theta 1 is 45 degrees. So we take r2 cross n2 plus m2 equals 0, and that we get m2 is 4 minus pi times r squared omega naught all over 8 times the square root of 2. If we want the shear and normal force here, we need to dot this with unit vectors in the circumferential and radial directions. So the radial unit vector is actually just this vector here. So we dot n2, so we have the two components of that, dot it with this, and then set theta 1 equals 45 degrees. And we get the shear force there is pi r omega naught over 8 times the square root of 2. And then in the circumferential direction, again, that's a vector perpendicular to this, so it's minus sine theta 1 cosine theta 1. And we take this dot product, and we get that the normal force is pi minus 4 times r times omega naught over the quantity 8 times the square root of 2. So we get the normal and shear forces there. Now we can just redo the same thing, but now we're going to take theta as 120 degrees. So I have F2 double prime, and again we get resultants here. I just did it numerically in this case because they got a little ugly. So the resultant in the x direction is minus 0.375 r times omega naught, and in the y direction it's minus 1.26 r times omega naught. The equivalent moment, the moment generated about this point from this distributed load, is again 0, because again all of these act through this origin. So we get N3, the internal force vector, must be minus F2 double prime. And the position vector here is R3, and that is crossed with N3 plus M3, must be 0. And again, this is just same as this vector here, but with this being 120 degrees now. And this gives us 3 equations and 3 unknowns. We'll get, obviously it's trivial to find N3 here, it's just the negative of this. M3 is 0.957 r squared omega naught. And then if we want the shear and the normal, we can again take the dot product of this internal force vector with the radial unit vector and with their circumferential unit vector. And we get that V3 is 0.907 r times omega naught, and the normal force is minus 0.957 r times omega naught.